Lesson 11.5, inverse matrices. So if you have a 2 by 2 matrix like this, A, B, C, D, there's this inverse matrix that's associated with it. And if you know the inverse matrix, you can use this to also solve systems of equations. Now, notice I'm only doing a 2 by 2 here, and that's as far as your book also goes, right? So can you take the inverse of a 3 by 3? Yes, you can, but looks like your book wasn't interested in going that far. We'll start because this one's a bit easier and gets the concepts across, right? And so what is the inverse? Well, you guys remember this right here represents the determinant. So it's 1 over the determinant, or you can say divide this by the determinant. And it looks like what I'm going to do here is swap the places of A and D, these corners on the top left, bottom right. Okay, and then the top right, bottom left, these BC terms, I'm just going to make those negative. Okay, so what would that mean for this to be an inverse? Well, one property is if you multiply the original matrix by its inverse, or it could be the other way, you'll get this identity matrix of 1, 0, 0, 1. Okay, so, that's another concept too, is this idea of an identity. Any matrix times the identity matrix 1, 0, 0, 1 will just produce the original matrix. Right? And then here's the 3 by 3 version, which I guess we're not going to quite get into, but that's what it looks like. Right, so here, I'll make up um, let's even just stick to ABCD, right? Because ABCD could be anything. They could be any numbers. Say if I multiply this by 1, 0, 0, 1. Okay. Again, this right here is called the identity matrix. Okay. I should get the original matrix out of it. Let's see if I do. So let's see, that's A times 1 plus B times 0. Oh, which of course is just A. It's A times 1 plus 0. Okay. How about this term over here? So this element. So I got A times 0, which is 0, plus B times 1, which is B. How about down here? Got C times 1. Okay, that's C. And then D times 0. Oh, well, that's 0. So C plus 0 is C. And then C times 0 plus D times 1 is D. Yeah, so this and this match. Right, so yeah, take a matrix, multiply by the identity, you get the same matrix that you started with. Okay. Now, how about this? Um, what if find an inverse, right? So here, this one, I'll put some numbers. Yeah, they got some examples coming up here anyway, so we'll run into some. Let's just go through their examples. All right, so example 1, determine whether each pair of matrices are inverses. Well, I think the idea we're getting at here is that if you multiply a matrix times its inverse, let's see, how did, yeah, okay, well, m and minus 1, okay. You guys get 8 in, okay. You should get the identity matrix, okay, which in the case of a 2 by 2 would just be 1, 0, 0, 1. Okay. So let's see if we get that out of these. All right, so we give us matrix A and matrix B. So let's go 2, 5, negative 2, negative 6. And multiply that by 3, let's see, 2.5. Can I make that 5 over 2? Is that right? And then negative 1, negative 1. Okay, so what would this be? Okay, I'm gonna have to add some parts here. Let's see what we get. So it's 3 times 2, which is 6, plus 5 times negative 1, which is negative 5. So plus negative 5 or just minus 5. So that's the first element. Okay, next element. 2 times 5 halves is 5. Okay, 2 times 5 over 2 is 5. Okay. And then plus 5 times negative 1, that would be minus 5. So there's the next element. Okay. So I got element 1, 1, element 1, 2. Now let's go to element 2, 1. So negative 2 times 3 is negative 6. And then negative 6 times negative 1 is positive 6. And then finally, negative 2 times 5 halves is negative 5. And then negative 6 and negative 1 is plus 6. Okay. Yeah, look how that cleans up. Watch this. Okay. So 6 minus 5 is 1. 5 minus 5 is 0. Negative 6 and 6 is 0. Negative 5 and 6 is 1. That is the identity matrix. Bing! So were these two original matrices inverses? Yes, yes, yes. These are inverses. Because by multiplying them together, we get the identity matrix. Yeah, so it works out. Correct. And if we got anything else, then they would not have been inverses. Well, how about example 2? Ooh, find the inverse. Okay, so now they're just gonna hand us a matrix, and how would we find the inverse from scratch? Okay, so we got um, matrix J got -4, 12, -3, 9. Okay. Now, I remember how to find the inverse, J, -1. So here, go and drop that down. Find the inverse matrix. Okay. So this is going to be equal to, well, it'll be 1 over the determinant. Right? Remember, this is determinant of J, or so 1 over that, right? Right. And then multiply by, right? Okay, so we got like a scalar multiple of, right? And I remember what I had to do was take these corners, these A and B corners, and swap places. So put the 9 up here and the -4 down here. And take the -3 and the 12 and just make those the negative of themselves. So this would be +3 here, and this would be -12 up here. Okay. All right, so it's coming together. But oh, really, I just gotta find this determinant. So what is the determinant of J? Okay. Well, remember that was like AD minus BC. So I'll go ahead and do that. So that would be -4 times 9 minus -3 times 12. I remember that from last week. Okay. So that would be -36. Oh, I got a double negative here, so that's plus 30, 36. Oh, wait, is that supposed to work out like that? E. Okay, okay. All right. I didn't realize that was where this was headed. Guys, are you allowed to divide by 0? Okay, so cannot divide by 0. Okay, so okay, so you're both making the claim here that the inverse does not even exist. So J inverse does not exist. Okay, well, I guess that can happen sometimes. Yeah, hopefully the next one does work out. Yeah, it looks like the next one they do have working out. So here we'll go ahead and do matrix. Hey, okay, it'll be the same process, but of course, we probably won't end up being divided by 0. And so we got k equals, we got -5, -7, 4, 6. Okay? So I'm going to say k inverse equals, well, it'll be 1 over the determinant of k, and that whatever scalar multiple times, right? These two elements swap places, so the 6 up here and the -5 here. And these two elements are going to become the negative of themselves, so +7 here and -4 here. Right. Well, I still got to find determinant k. So determinant k, that could be -5 times 6, and then minus, and then 4 times -7. Okay. Which is like -30. Ooh, we got a double negative. I'll say plus, and that would be 28. So -2. So that is the, here's another way to write that, determinant k, right? Determinant of matrix k. Right? Okay. Remember, these determinants come up to hard number values like this. So now we can put this up here. So back to the original puzzle we're trying to solve here. 1 over -2 times then 6, 7, -4, -5. Okay. So let's see. 6 over -2 is -3. 7 over -2, but you're writing this an improper fraction. You could do a decimal if you like, -3.5. Negative over negative, the negatives cancel 2. And then over here. Okay. So I think this right here should be the inverse. Let's check the text and just confirm that they got the same thing. I just got -3. So it has two. Yeah, yeah, exactly the same. They even left the improper fractions there. Yeah. So there you go. There's the process. Okay. That's how you find the inverse. Okay. So recap so far. You're looking at how to find the inverse, right? We're just focusing on 2 by 2 for this class. We're gonna swap these elements and make these elements negative, and then multiply the whole thing by the scalar multiple of 1 over the determinant. And so we did that. Going back a little bit, you guys remember that if you multiply a determinant by its own inverse, you always get this identity matrix of 1, 0, 0, 1 for a 2 by 2. Okay? But there's one more thing I think it's interesting that you can do with this, and that's to, here we go. Okay. You can solve systems of equations, and hey, we got a nice story example here. So let's do a story example. We got a metal alloy is a combination of 2 or more elemental metals. For example, copper and zinc can be combined to make brass. Ooh. How the ally will be used determines the best ratio of copper and zinc. So I guess if uh, we're making this, well, this be a trumpet here, or whatever this brass instrument is. Maybe you want a particular mix of copper and zinc, but maybe if you're making something different, maybe something structural, you want like a different uh, mixture, like proportional. A sheet of yellow brass commonly used to make musical instruments contains C pounds of copper and Z pounds of zinc, and weighs 16.4 pounds. Ooh, that looks like the copper plus the zinc. When the price per pound of copper is $3, so $3 a pound for copper and $1.10 per pound for zinc, right? The cost of this is $38.94. How many pounds of each metal was used to make the yellow brass? Right? So uh, I know I'm going to say C equals number of pounds of copper, and let's have Z equal number of pounds of zinc. All right. Now I can make a system of equations out of this, and then I'll show you how to turn it to a matrix and solve this. All right, so I know that if I add together the number of pounds of copper plus the number of pounds of zinc, I'm getting 16.4. As I have 16.4 pounds of metal altogether. Now, if that's my only equation, then I don't know how much of each one. Maybe it's a lot of copper and very little zinc, or vice versa. I don't know. But if I bring in the prices, make a second equation, then I'll be able to solve this. $3. Wait, why did they switch to zinc and copper? Okay, wait. Right. So, oh no, $3 a pound for copper. That's what it is. Right. So $3 a pound for copper times the number of pounds of copper plus $1.10. So I'll say 1.10 or 1.1 per pound times the number of pounds of zinc. You can see if we do dollars per pound times number of pounds, we're getting some number of dollars. So it costs this much to buy all the copper, and it costs this much to buy all the zinc. And you put it all together, and altogether it costs $38.94. Now I'll drop the dollar sign, but otherwise, yeah, that's it. So this right here is your system of equations. Okay? Now, you could go back to maybe old methods. You could use substitution or elimination, right? To solve, right? How much copper, how much zinc. But how could you solve this with a matrix? So somehow I need to, here, well, watch this, just go with this. If I take these coefficients, these four coefficients, two here and two here, and I turn it into a 2 by 2 matrix. So I have a coefficient of 1, a coefficient of, again, 1, and then 3, and then 1.1, right? And I do my matrix multiplication of, I'm going to call CZ, right, copper and zinc. Right? I should get this 2 by 1 matrix outcome of 16.4 and 38.94. And these are like dollar values, or well, hold on. What do you figure? Yeah, this one's pounds, this one's dollars. Right? Anyway, the numbers are still there. Right? Now, watch how, because you got to remember how to multiply matrices. Here, I have a 2 by 2 matrix here and a 2 by 1 matrix here. The fact that these twos match means, bing, yes, I am allowed to multiply. And this outside 2 and this outside 1 tell me that the product matrix should be a 2 by 1, which bing, it exactly is. Yes, that's good. Now, remember, I'm going across the first matrix and down the second matrix. So here's C, so 1C plus 1Z equals 16.4. Yeah, that's exactly what my first equation says. So it works. Doing this leads to this number here, which is the first equation. How about the second equation? 3 times copper plus 1.1Z should be 38.94. Yep, and that's exactly what my second equation says. All right, so this is a nice matrix representation of this classic looking system of equations. Right? So now, great, how does that help us? Right? Well, here's where inverse matrices are going to come in. Right? Like what if this is some matrix M, if I simply multiply both sides by its inverse, then the inverse times the original matrix will give me an identity here, which will effectively just cancel out and leave it with C and Z. And it'll be C and Z equal, and I'll have a 2 by 1 matrix here, which will be the answer. And that's it. Okay. So let's find the inverse matrix. Okay. See if I call this M for matrix, right? So M1 for inverse. So find inverse matrix. Okay. this is going to be equal to, so 1 over the determinant of the matrix, and multiply by, and then, see, I need to swap these two, 1.1 and 1, and then make these negative, -3 here and -1 here. Right, so I'm getting a little closer. Right, but what is the determinant? So the determinant will be 1 times 1.1, 1 times 1.1, minus 3 times 1. Which is it's 1.1 minus 3. -1.9. Okay, I can go with that. Yeah, give them some decimal looking values. That's all right. Keep going. Okay. So now I just need to take this value and plug it in right here for this m, right, and then go on my way. Right, so I'll take time here. Right, so picking up from here, I'm gonna get the so inverse matrix is equal to 1 over -1.9, and that's a scalar multiple. 1.1, -1, -3, 1. Right. So, okay, these are gonna be kind of funny numbers. I wonder if I should just leave them as fractions. Like, yeah, let's go ahead and do that. Right. Right. So let's call this -1.1 over 1/9. And then, well, these negatives are going to cancel. So 1 over 1/9. And then these negatives also cancel, 3 over 1/9. And then -1 over 1/9. Okay, there's my inverse matrix. Okay, great. So now I know my inverse matrix. Okay. And see, the method we're going with here is if I multiply, maybe I'll switch to the blue ink right here. If I multiply the inverse matrix right here and right here, right? I'm effectively doing the same operation on both sides, but it's going to create an identity on the left side. Let's just go leave it with the C and Z. On the right side, I'll get a couple of numbers, which will be the answer. They'll tell me how many pounds of copper and zinc did it have to use. And so let's do that. All right, so here, I'll do the whole thing out here, so you can really see how this is going to work. All right, so -1, 1 on 1/9, 1 on 1/9, 3 on 1/9, -1 on 1/9. Okay, that's being multiplied by 1, 1, 3, 1, 1. Okay, and then I have a CZ and equal to, okay. Well, I multiplied my inverse matrix on the left side, so I have to multiply on the right side right here to balance the equation. So I got my -1, 1 on 1/9, 1 on 1/9, 3 on 1/9, -1 on 1/9. And that's multiplied by 16, 4, and 38.94. Okay, so that should be set up. All right. Now, if I go through our process, I really just want to confirm that this will be an identity right here, right, on the left side. Okay. And maybe if you've done enough of these and you don't think you're making any mistakes, then it's a good kind of shortcut step you could go through. Right? Let's try this. Okay, so if I have -1, 1 on 1/9 times 1, and then plus 1 over 1/9 times 3. Here's oops, the typo right here. Okay, times 1. Where's my plus? There, need a plus right here. Okay, there we go. Yeah, that worked out. Okay. Okay, so yep, that would be the element that you would need for the identity matrix. That's looking good so far. That's good. Okay. All right. How about this element 1, 2? So we got -1, 1 on 1/9. Let's check this here. Okay. Times 1 plus, and then this right here, 1 on 1/9 times 1.1. That gives me 0, 0. Yep, working good. Now, next, got 3 over 1/9 times 1, 3 over 1/9 times 1, plus, and then, actually, it's a negative. 1 on 1/9 times 3. That also gives me 0. Okay, so we're good. And then finally, 3 over 1/9 times this one over here, plus negative 1 on 1, 9 times 1, 1. Yeah, okay. Yep, it definitely gave me the identity matrix. This is exactly what I was looking for. It just means I haven't made any mistakes in this process. Okay. So you can also treat everything to the left side of the equation here is just C and C. That's it. Okay. How about over here? Okay. Now notice I have a 2 by 1 matrix, or sorry, 2 by 2 in that, and this one's a 2 by 1. Okay. So the fact that this 2 matches this 2 means that, bing, yes, I can multiply. So if I tried to multiply it in a different order, it would fall apart. It wouldn't even be allowed. So I do have to put the inverse matrix in front like this. Okay, and then my product is going to be a 2 by 1 matrix. So 2 by 1. So that's what I'm looking for. All right, so let's put this together. Negative 1, 1 on 1, 9 times 16, 4 plus 1 on 1, 9 times 38, 9, 4. So, ooh, a nice even 11. Wow. Okay, so maybe like 11 pounds of copper I think I have to buy. Yeah. And then how about this next element? 3 over 1, 9 times 16, 4 plus, and then negative 1 on 1, 9, 1 on 1, 9 times 38, 9, 4. Is that, let's see, is that, make sure it's what they got here. We'll check that. Okay, dang, good typing. Ah, yeah. Oops. He's having trouble pressing these buttons today, so that should have been there. Okay, boom, boom. Double check, make sure. Yeah. Okay, that's what they got. There we go. Boom, boom. Okay. So the answer is 11 pounds of copper and 5.4 pounds of zinc. Okay, there you go. Right. Now, if you wanted to go to a classic way of solving system equations, or take these answer values and plug them back into the original equations, of course you can confirm with the answer, but yeah, there you go. That's it. All right. So now you guys learned, let's do a recap of what you guys have seen. All right. You guys know that the identity matrix is 1001, multiply any matrix by the identity itself. So we got that. If you multiply a matrix by its inverse, you should get the identity matrix. Right? But how do you find the inverse matrix? Right? So it's 1 over the determinant times, right? Now, and then for a 2 by 2, see, we're going to swap these elements from the original, right? And then make these negative from the original, right? And then scalar multiply that. Okay? Finally, you guys saw that you could set up a system of equations and solve that using matrices like we did right here.